So what's the main idea behind Newton's first law of motion? Well, here's the gist of it. An object at rest stays at rest, and an object in motion continues in motion unless acted on by a net force, that is, a non-zero net force. So let's illustrate this. Let's say if I place a block on the ground, let's say a 5 kilogram block, and it's at rest. That block is going to stay at rest unless you push it. If you don't apply a force, that block is going to stay where it is. However, if you apply a force, and if that force is strong enough, the block will begin to slide across that surface. And so if you want to cause an object to move, it requires an action. A force is basically a push or pull action. You can push the box to the right, or you can pull it with a rope. Either case, a force is required to accelerate the object. If no force is applied to the object will remain at rest. Now, what about the second part? An object in motion continues in motion. Imagine a carpet floor. And let's say you place a ball on this floor and you give it a push. So the ball is moving. What's going to happen if you roll a ball against a carpet floor? That ball will eventually come to a stop. Now, why is that? Because Newton's first law states that an object in motion continues in motion unless acted on by a force. Why does the ball, when it's rolled against a carpet, comes to a stop? The reason being is there's friction between the ball and between the carpet. And so friction is a force that opposes motion. Friction always causes objects to slow down and eventually come to a stop. So there is a net force acting on the object, and that is its friction. Now let's say if we can reduce friction. So let's say if, instead of rolling the ball on a carpet surface, let's say if we can take it and give it a push along smooth ice. So imagine if there's a lake and it's cold outside, it's wintertime, and the lake freezes over, and you take a ball and you roll it against an icy surface. What's going to happen to the ball? Will it come to a stop? Now, going back to the carpet example, if you roll the ball against the carpet, the ball is not going to travel very far. It's quickly going to come to a stop. It might travel a few meters, but it comes to a stop. Now, if you roll the ball against an icy surface, it's going to roll for a very, very long time. It's going to travel a huge distance before coming to a stop. Now, granted, there's still friction on the icy surface, but that friction is a lot less than what you'll find against a carpet. And so that's why the ball is going to travel for a very long time. It's going to keep going and going and going. And eventually, after a while, it's going to slow down and come to a stop. But it's just going to take a long time to come to a stop, because the friction that's on the icy surface is a lot less. It's still there, but it's a lot less. Let's say you and your friends decide to hang out. You decide to go to the bowling alley, and it's your turn to roll the bowling ball. As you roll it towards the pins, whatever direction you roll it to, the ball will travel in that direction. So let's say, let me clear this away. So let's say this is you, and you have the bowling ball in your hand, and you're trying to, let's say the pins are right here, and you have to keep it in this lane. You could try to roll it fast or slow, but eventually the ball is going to make it to the pins. Your task is to aim it correctly. For instance, if you aim the ball this way, if you aim it straight, you'll notice that the bowling ball will continue to go straight. in the direction that you aim it. An object in motion will continue in motion unless acted on by force. So the surface is pretty smooth, so friction is reduced to a minimum. So the only force that's acted on the ball is the initial push that you give it. Other than that, it just continues in the direction that you send it. Now let's say if you send it at an angle, that ball will continue to travel in the angle, and then you're going to strike out. So you're going to miss the pins. And this is a good illustration that highlights this second part of Newton's first law. If you roll it towards the left or towards the right, you know it's going to go straight and reach the edges, and you're going to miss the pins. The only way to get those bowling pins is you have to aim it straight. And if you aim it straight, it's not going to veer off to the left, it's not going to veer off to the right. If you realize if you started out straight, that ball is going to continue traveling straight. It's going to continue in the motion or in the direction that you send it. So you're in control of what direction you send it. Now, what are some ways in which we can reduce friction altogether? Is there a way that we can eliminate friction? Because whether you're bowling a ball on a smooth surface or if you're rolling it on an icy surface, even though friction is greatly reduced, it's still there. So if you roll an object, it's not going to continue forever. Eventually, it will come to a stop. But can you think of any examples in which friction is so greatly reduced you could say that it's almost zero? One example is space. Outer space is virtually empty. There's hardly any molecules in outer space. So if you were to throw a ball in outer space, that ball will continue to travel unless it encounters another object. It's just going to continue traveling straight. As long as it's not affected by the gravity of a nearby planet or a star, that object will continue straight. So let's say, for example, let me clear this away. So imagine if you're an astronaut in space and you're pretty far away from Earth. There's no planets around you, no solar systems, no stars, nothing. All there is just you and a ball in your hand. Now, let's say you decide to throw the ball. So what's going to happen once you throw the ball to the right? The ball is going to travel in the direction that you throw it. So if you throw it this way, it's going to travel. You're going to feel something that pushes you back based on Newton's third law. For every action, there's an equal and opposite reaction. So if you throw the ball to the right, you're going to push back towards the left. So as you throw the ball to the right, if that ball doesn't encounter an asteroid or some other object, it's going to continue to travel at the speed that you gave it. So it's not going to change direction. It's not going to go that way. It's simply going to continue in the motion as set forth by you. So it's just going to go straight. Kind of like that bowling ball example. But in space, friction is virtually non-existent. So that ball will keep on traveling in that direction until it's acted on by net force. That is, unless it hits or collides with another object, or if it enters the gravitational field of another planet. Now let's say eventually it comes next to a planet. Let's say this is Earth. Then gravity is eventually going to turn this object towards Earth. And so a net force can change the motion of the object, but if there's no net force, the ball will continue to travel straight. Now, I want to give you a few situations, and I want you to determine if there's a net force acted on an object. So let's say ball A is moving straight at constant speed. If ball A moves straight to the right at constant speed, is there a net force acting on the object? The answer is no. There is no net force. Now, let's say ball B is moving straight to the right, and let's say initially the speed is 20, and then 1 second later, it's 25. So ball B is accelerating. Is there a net force on the object? The answer is yes. Anytime an object is accelerating, or anytime the speed is changing, there is a net force. Now, if the speed of the ball changes by 5 meters per second in 1 second, that means that the acceleration is 5 meters per second squared. Acceleration is the change in velocity that occurs every second. It's how fast the velocity changes every second. So if it goes from 20 to 25 in 1 second, the acceleration is 5. Now, let's use a third ball, ball C. Now, ball C is traveling at constant speed, but it's turning at constant speed. Let's say it's moving at 20 meters per second, but it's turning as it does so. Is there a net force acting on this object? Now, notice that ball C doesn't continue in one direction. It's changing direction. So anytime an object changes direction, there is an acceleration. That acceleration is perpendicular to the object, and the net force is always in the direction of the acceleration. So there is a net force. So just because the speed is constant doesn't mean the net force is zero. The only way the net force is going to be zero is if the object is not moving at all, if it's at rest, or if it's moving at constant speed in a single direction. If the direction changes, it's because there's a net force. A force causes an object to change its motion. It can change in two ways. The force can cause the object to change its speed. It can speed up or slow down. Or the force can cause the object to change direction. When you think of, let's say, the sun, let me use a different color to represent the sun. And let's say this is Earth. Earth is relatively small to the sun. Earth moves relatively at constant speed around the sun, for the most part, on average. However, it's constantly changing direction. And that's because of gravity. The gravitational field that's acting on the Earth due to the sun causes the Earth to move in a circle. So the Earth moves at constant speed, but gravity, the gravitational force generated by the sun that's acted on the Earth, pulls the Earth towards the sun. And so instead of the Earth just traveling straight towards outer space, it turns. So keep in mind, there's always a force of gravity between two objects. The Earth also exerts a gravitational force on the sun. And these two forces, they're equal, according to Newton's third law of motion. For every action force, there is an equal and opposite reaction force. So, a force doesn't have to speed up an object or slow it down. It can also change the direction of the object.